All right, let's be honest. That periodic table you had to memorize in school, kind of boring, right? Well, let's just forget that chart for a minute, because today we're going to look at it in a totally new way. We're going to treat it like a map, maybe even a treasure map, that shows us the secrets of literally every element in the universe. So let's dive in. So what if the periodic table wasn't just a grid of boxes? What if it was a real map, with mountains of reactivity and deep valleys of stability? That's exactly what we're going to explore. And the coolest part? This whole map follows a hidden logic, a set of patterns that are so predictable they explain, well, pretty much everything about how elements behave. Now, these patterns have a name, of course. Scientists call them periodic trends. But let's stick with our map idea. Think of these trends as the lay of the land, the topography of our element map. Just like on a real map, if you know which way you're going, you can pretty much predict what kind of terrain you're about to run into. And here's the kicker. All of these seemingly complex patterns, all these different properties we're going to talk about, they all come down to one thing: an element's basic, fundamental atomic structure. It's all about what's going on deep inside the atom. Okay, so before we just start wandering around this map, we need to know how to read it, right? We need the map's key, or as I like to call them, the rules of the road. And here's the great news. There are only two fundamental rules you need to know. Two key directions of travel that explain everything else. If you get these two, I promise the rest is a piece of cake. All right, rule number one. It's all about pulling power. It's called the nuclear charge. And it's super simple. The more protons you have in the center of an atom, that nucleus, the stronger its positive charge is. Think of it like a magnet. A stronger magnet is going to pull all those negative electrons in a lot more tightly. And rule number two, it's all about size. See, electrons aren't just buzzing around randomly. They live in these specific energy levels. Scientists call them shells. The best way to picture it is like the layers of an onion. And every time you add a new shell, a whole new layer, the atom just has to get bigger. It's that simple. Okay, so let's put that together. Those are our two directions of travel. When you go across the map from left to right, what are you doing? You're adding protons. You're cranking up that magnetic pulling power. But when you travel down the map, you're adding whole new layers, new shells. And that's it. Those two simple rules, they are the why behind literally every single trend we are about to see. All right, we've got our rules of the road, we know how to read the map. Let's start exploring. First stop, we're going to look at the most fundamental properties of any element out there. Just how big is it, and how strong is its grip on its own electrons? So, first things first, size. The fancy term for this is atomic radius, and it is exactly what it sounds like. It's just the distance from the very center of the atom, the nucleus, all the way out to its farthest electron. This is the literal size of each square on our map. And check this out. This is where our two rules of the road just click into place perfectly. Remember how going across the table increases that nuclear charge? Well, that stronger pull acts like a winch, just reeling those electron shells in tighter and tighter, which actually makes the atom shrink. Kind of weird, right? But then, when you move down the map, you're just adding another layer to that onion. So, of course, the atom has to get bigger. See? It all makes perfect sense. Okay, next up, let's talk strength. We call this ionization energy. And honestly, the best way to think about it is as a measure of an atom's grip. How tightly is it holding on to its electrons? It's the amount of energy you'd have to spend to rip one of its electrons away. So a really high ionization energy means that atom has a death grip on its electrons. So how does this play out on our map? Well, just think it through. Those smaller atoms over on the right side of the table, their electrons are super close to that really powerful nucleus, so their grip is going to be crazy strong. But as you go down the map and the atoms get bigger, those outer electrons are so far from the center, they're just way, way easier to pick off. Okay, so what happens when an atom is in a bond with another atom and they're supposed to be sharing electrons? Well, that's where electronegativity comes into play. You can think of it as a chemical tug of war. It's a measure of how good an atom is at pulling shared electrons toward itself. And I bet you can already guess how this trend works, right? You've got a really strong nuclear charge packed into a tiny little atom. Well, that's the perfect recipe for a powerful pull on any electrons nearby. But as the atoms get bigger and bigger as you go down the map, that central pull just gets weaker over that long distance. It's just like how a real magnet works. And hey, fun fact for you. If you're looking for the undisputed heavyweight champion of this chemical tug of war, look no further than the top right corner of our map. It's fluorine. Fluorine is the most electronegative element of them all. It is the king of grabbing electrons. Okay, so we've got a handle on size and pulling power. Now let's see how that actually affects the way elements interact with each other. We're going to start mapping out the trends for gaining and losing electrons, which, let's be honest, is the heart and soul of pretty much every chemical reaction. So think back for a second. We said ionization energy was the price you pay to take an electron. Well, electron affinity is kind of the opposite. It's the reward or the energy payoff an atom gets when it successfully gains an electron. It's basically a measure of how much an atom wants to grab an extra electron. Now, I know that term more negative can sound a little weird. All it means is that the process is more favorable. Think of it like a bigger energy payout for the atom. And that makes sense, right? As you move across the map to the right, those atoms are just 1 or 2 electrons shy of having a full outer shell, which is like the ultimate goal for an atom. It's super stable. So gaining that last electron is a massive win for them. But for those bigger atoms further down, their pull isn't quite as strong, so the energy reward for gaining an electron is a little less exciting. And finally, let's talk about what actually makes a metal, well, a metal. The defining trait, what we call its metallic character, is its tendency to lose electrons. Metals are givers. They are more than happy to give up an electron and become a positive ion. And again, I think you can see where this is going. Since those atoms on the far right hold their electrons so tightly, remember they have that high ionization energy, they are absolutely not willing to give them away. They're not very metallic at all. But as you go down the map, the atoms get bigger and they lose those outer electrons really easily, so they become more metallic. See? It's all connected. All right, we've hiked through all these individual trails on our map. We've checked out all the landmarks. We've seen how size, strength, and this whole game of giving and taking electrons, how it all changes in really predictable ways. So now it's time to pull back, zoom out, and take a look at the whole complete map. And there you have it. Just take a second to look at that. It's actually kind of beautiful, isn't it? Look at how atomic radius, the size, trends in the exact opposite direction of almost everything else. And see how ionization energy, the grip, and metallic character, the willingness to let go, are perfect opposites? This isn't just a random list of facts. It's a single, elegant, interconnected system. So why does any of this matter? What's the big takeaway? It's this. This map is incredibly powerful. It gives us the ability to predict things. Just by knowing where an element lives on this map, we can make a really good guess about its size, its strength, and how it's going to behave and react with everything else. This isn't just a neat trick. This is the fundamental logic that all of chemistry is built on. And that really leaves us with one last kind of mind-blowing thought. We've just seen that this entire complex map is really governed by just 2 incredibly simple rules. So the big question is, how? How do these simple, predictable rules combine in a way that creates the endlessly complex and beautiful world we see all around us? You know, the rocks, the air, even us. That, right there, is the magic of chemistry. Thanks for exploring the map with me.